All right, here's going to be a quick video on Euler's method. It's a BC topic, and I want to make sure we go over it. So, this is a general graph. It's a smooth curve, and Leonhard Euler, this mathematician, devised a way to approximate this curve by taking a point, finding the slope at that point, and then going a certain amount of x value. We're going to call that a step, or a difference in x. And basically, he multiplied the slope, the rate of change, by the step. And remember that distance is rate times time. You think of the step as the time. The slope times that difference in h, or difference in x, gets me the difference in y. I'm going to say that one more time. If I start at a certain y value and I add the slope dy dx multiplied by a change in x, or a step times slope, that gets me a change in y. So essentially, once he does that step and multiplies its slope and goes up, we get a new point. I'll call this x1, y1. And Euler does the same process. He finds the slope using a differential equation. He calculates the slope at that point. He goes a certain step out, multiplies that slope by the step h, and then gets a new y value, which is called x sub 2, y sub 2. And you kind of get an approximation of the smooth curve by using individual tangent lines. Let's use Euler's method to approximate the particular solution of the differential equation y prime equals x minus y passing through the point 0, 1. Use a step size of 0.2 or 2/10. That's going to be important. I'm going to call that my delta x. That's going to be how different my x is every single time. We also know what the slope is. I'm going to call that y prime. Of course, that is the slope, or the dy dx. All right. And then we have an initial condition. It tells us that it goes to the point 0, 1. And that's going to be x sub 0 and y sub 0. Now when I do Euler's method, I make a little table. Okay, so here's my little table. And in each column, just like you'd imagine, I'm going to label this an x and a y. I'm going to get values according to Euler's method. The first value I'm going to put in there is 0, 1, because that's where I start. Now, to get the next x value, I'm going to call it x sub 1. I will take whatever I had, x sub 0, and add delta x, or the step. And to get x sub 2, I would do the same process. This is called a recursive process because I just keep doing the same thing. And you can see how I'd calculate the rest of the x's. You just take the one before it and add the delta x. So in this case, where did I start? I started at x equals 0. And I'm going to add the step size, which is 0.2. And my next x value is 0.2. Now to get the new y value, it's slightly different. To get y sub 1, I get the y that I started with, y sub 0, plus that slope, and I'm going to call it dy dx, multiplied by the change in x, the delta x. Now the y value I started with was given to me. It's 1. Plus, and I'm going to use color coding here to help guide us. I started with 1. All right, and then I added a change in x multiplied by a slope. The change in x, of course, is 0.2 like it is every single time because it tells us the delta x, the step size, is 0.2 or 2/10. Now to calculate the slope, I'm going to need to take the x value minus the y value because that's how I calculate dy dx or y prime, is take x minus y. Now which x and which y do I subtract? Well, I'm on the second step right now, right? I'm in the purple step. So I'll use the points before to calculate the slope at the orange point, 0, 1. So x minus y would be 0 minus 1, negative 1. That's my slope. So I have my original y value plus the slope at that y value, which was negative 1, multiplied by 0.2. So I have 1 plus negative 0.2 or negative 2/10. And so my new y value would be 0.8 or 8/10. And then we repeat the process. So x sub 2 would be the x value I was at before, plus the change in x, which was 0.2 like it always is. And I get 0.4 as the next x value. To get the next y value, y sub 2, I take the y value that I had before. So I'm not using 1 this time, I'm using 0.8. that's where I left off, plus the slope at that y value at 0.8. To get the slope, I would calculate using the differential equation, y prime equals x minus y, and then I get 0.2 minus 0.8 multiplied by the step size, which is always 0.2 in this problem. So I have 0.8, the old y value, plus negative 0.6, or negative 6/10 times 0.2. So 0.8 minus, and that'd be 0.12. So I get 0.68. And that's my new y value. Because I had the 0.8, 8/10. I added the rate times time, or in other words, the slope times the difference in x, which gets me a difference in y, right? Because these dy dx's kind of cancel out, if you want to think of it that way. Y plus a change in y gets me my new y value. And those are my 3 iterations of Euler's method. To approximate y of 0.8, that means that x would have to be 0.8, and I need to do 2 more iterations of this. Okay? So 0.6. That's the next one. Why? Because x sub 3 would be x sub 2 plus the delta x, and x sub 2 was 0.4 plus 0.2. I guess technically this is the 3rd iteration, so I apologize, but that's okay. Let's keep going. Y sub 3 equals the y value I left off at, 0.68, plus the slope times the step size. And notice that the step size every single time was at 0.2. The slope changes though, because now I have to use the point I was at, 0.4 minus 0.68. 0.68 plus, and this becomes negative 0.28 times 0.2, 0.68 minus 0.056. I'm going to add a 0 to make this easier to subtract, and I get 0.624, and that's my new y value. And so now I've done 3 iterations. I'm going to do 1 more so I can get to that 0.8 approximation. And I'm going to go ahead and pick up where I left off. 0.624. This will be my 4th y value. And it's going to be plus the slope at the point right before it times the slope size. So the slope at the point right before it using this equation, x minus y, would be 0.6 minus 0.624. And so it's 0.624 plus negative 0. Oh boy, so it's going to be 600, 0.024 times 0.2, 0.624 minus 0.0048, an extra 0, and I get 0.6192. And that's the estimate when x is 0.8, I would get 0.6192. And this is Euler's method. You're essentially just using this process to estimate what the next x values and next y values are going to be. Let's do another one. So in this case, consider the differential equation dy dx equals xy with the condition y of 0 is 1. So my initial point, 0, 1, that's going to be my x sub 0 and y sub 0. Use Euler's method with 5 steps of 2/10 size to approximate y of 1. So in my table, we're going to start with my initial x value, which is going to be 0, and my initial y value, which is going to be 1. And I'm going to do 5 steps of 0.2, 2/10. I do another step of 2/10, 0.4, a third step, 0.6, a fourth step, 0.8, and the fifth step, 1.0, to get to where I need to go. All right? So now let's go ahead and use this process. So I have all the x values, so I'm just going to focus on the y values. So to get y sub 1, the first iteration of this rule, I take the original y value, y sub 0, plus the slope at that point, dy dx, multiplied by dx. All right, so to get y sub 1, I take my initial x value, 0, plus the slope of that x value. So at that x or y value. So in this case, it has both x's and y's in the slope formula. So I'd take the x times the y for that point. So the y value actually should be 1. My apologies there. Made a typo thinking about what I was trying to say and not writing what I was trying to say. Or something like that. I take 0 times 1 is 0. The change in x is 0.2. This ends up being pretty easy. It's just going to be 1. So my first y value is 1. Let's find the second y value. The second y value would be where I left off, the 1, plus the slope at this point that's green, 0.2 times 1, because that's the formula for the slope. X times y, I get 0.2, multiplied by the step size, 0.2. 1 plus 0.04. And I get 1.04 as my second y value. Time to get the third y value. Y sub 3 is where I left off. 1.04 plus the slope at that point, which would be 0.4 times 1.04. Don't have a calculator with me right now, so I'm just going to multiply this by hand. And I get 1.416. There are 3 decimal places, so I move the decimal point 3 places. 0.416. Got the 1 in there. Multiplied by the step size, 0.2. So I have 1.04 plus looks like 0.832. And so I add those together. 0.0400 and then 0.0832. So then I have to subtract by borrowing. Good old subtracting, old-fashioned way. Borrow again. So I borrow that now. 13 minus 8 would be 5, 9. So now I have 0.9568. And you'd go through this process until you get to the next y value that you need. So I don't have a calculator, so I'm not going to make you watch me do a bunch of mental math, but I hope you get this iterative process where you take the y value from before, add the slope at that y value before, multiplied by the change or step size 0.2. Okay. Now eventually a common practice is that on the AP exam you might be asked to separate and integrate. So I'm going to have 1 over y dy dx, and what we're going to do is solve this differential equation and get the exact answer and compare our estimates. So I get the natural log of the absolute value of y plus some constant of integration c, and then I get x squared over 2 plus a different constant of integration, which leaves me with, if I wanted to, combine the two c's, I get 1/2 x squared plus a new c. Solving for y, I get y equals e to the 1/2. And you could have plugged in the initial condition before this, like we did in class, but that's okay. Which gets me y equals c e to the x squared over 2. Now it tells us the initial condition, just like before, is when x is 0, y is 1. So I put 1 in for y, I put 0 in for x, and I get 1 equals c e to the 0 over x, 0 over 2 squared, 0 squared over 2. So 1 equals c times 1. So I get y equals e to the x squared over 2. And now I can compare our estimates to the function using Euler's method to what the actual function is. The actual solution is y equals e to the x squared over 2. And so this is the exponent. So I can even plug in like 0.4 or 0.2 and compare it to this. All right. So that's Euler's method. I hope that was helpful. Let me know if you have further questions.